Thank you all for joining this talk. Today, I'm excited to present our work, titled Splat 4D, Diffusion-Enhanced 4D Gaussian Splatting for Temporally and Spatially Consistent Content Creation. Our goal is to address a central challenge, generating high-quality 4D content that is both visually compelling and temporally stable. Let's begin with some background. In the domain of object-centered 3D generation, researchers have explored a variety of approaches. Some methods start from the perspective of novel view synthesis. For example, MVDream is a diffusion-based model that enforces multi-view consistency and has been effectively adapted for 3D generation. Another line of work focuses on generative Gaussian splatting, such as Dream Gaussian, which leverages splatting techniques to produce radiance fields directly. More recently, large-scale models like LGM, the Large Multi-View Gaussian model, have been proposed for feed-forward 3D generation, enabling high-resolution content creation through multi-view training. Shifting to 4D generation, there are two main strategies in current research. One involves optimization-based methods that rely on SDS loss, such as Dream Gaussian 4D. The other builds on feed-forward pipelines, extending 3D generation frameworks to 4D, as seen in models like L4GM. Despite the progress, these approaches continue to face three major challenges: achieving time-efficient yet high-quality 4D generation, maintaining both temporal and spatial consistency, and handling complex, human-related features such as loose clothing. To overcome these challenges, our motivation is twofold. First, we aim to enhance visual quality by introducing an image enhancer that boosts fidelity and recovers fine-grained details. As illustrated here, after enhancement, even subtle textures, like the folds of a rose, become much more vivid. However, this enhancement process can easily disrupt the spatial and temporal consistency of the sequence. So a new question arises: how can we preserve coherence across time and space, even after applying visual refinement? We leverage a video diffusion model to refine 4D consistency, ensuring that the enhanced results remain smooth and stable across frames. This leads us to our proposed method, Splat 4D. At a high level, Splat 4D is a flexible 4D generation model that supports multiple use cases. It can generate dynamic 4D objects from a single monocular video. It can also synthesize 4D human motion given an input image and a motion sequence. With the support of the video diffusion module, Splat 4D can go even further, generating 4D content from a single image or a text prompt, and even performing text-guided 4D editing. For example, as shown here, we can edit the input to produce results like a rocket launching or Wall-E on fire, with coherent temporal evolution. On the next slide, we show more examples of high-quality 4D results generated by Splat 4D. For image-to-4D generation, we showcase results such as a spaceship, eagle, mushroom cloud, and dragon. For text-to-4D generation, we present examples including candle, jellyfish, Pikachu, and Kung Fu Panda. Next, we introduce the framework of our model. In the first step, we take an input image and use a video generation model, specifically Stable Video Diffusion, to generate a sequence of frames. We then apply MV adapter to synthesize novel viewpoints, resulting in a multi-view image sequence from 4 orthogonal directions. In the second step, we enhance the visual quality of the sequence using an image enhancer, which helps preserve and recover fine details across frames. As shown in the example, the enhanced image of the dragon reveals significantly richer texture and finer details. The third step involves converting the multi-view image sequence into a sequence of Gaussians. This is done using an asymmetric U-net, which transforms the image inputs into a stack of Gaussians representing a coarse 4D structure. To summarize, we first enhance each frame and each view using an image enhancer to recover fine details. Then, we transform the resulting multi-view image sequence into a sequence of Gaussians using an asymmetric U-net, producing a coarse 4D representation. However, because the enhancement and multi-view generation steps may introduce spatial and temporal inconsistencies, further refinement is necessary. In the fourth step, we address this inconsistency through an optimization loop. We first predict uncertain or inconsistent regions using an uncertainty prediction network, and mask out those areas accordingly. These masked sequences are then passed into a video diffusion model to in-paint and recover the missing content, producing a denoised and temporally coherent video. Finally, we use this refined video to optimize the original Gaussian sequence, improving both spatial quality and temporal stability. Additionally, our framework supports text-guided editing through the Instruct Pix-to-Pix network, enabling users to manipulate the generated 4D content using natural language instructions. Next, we present the generation results of Splat4D. We begin with monocular video to 4D object generation. On the left, you see the input video, which features a dancing robot. On the right is the generated 4D dynamic object. We rotate the 4D reconstruction to better visualize its geometry and motion from different angles. On the next slide, the left side shows a video of a blooming rose. On the right is the corresponding 4D object generated by our model. The structure and fine details of the rose are well preserved. The next two examples show 4D results generated from dog videos. As you can see, the 4D details are clearly captured, and both spatial and temporal consistency are well maintained. The next two examples demonstrate 4D generation from a single image. With the help of a video diffusion model, we first generate a short video from the input image, and then follow our pipeline to generate the corresponding 4D object. Here shows results for an eagle and a fire-breathing dragon, which validate the effectiveness of our approach. Similarly, our framework supports text-to-4D generation. As examples, we present the results for jellyfish and Wall-E. In both cases, the generated 4D content exhibits strong spatial and temporal consistency, along with high visual quality. Next, we demonstrate text-guided editing of 4D objects. In the first example, we begin by generating a 4D representation of a rocket using our image-to-4D pipeline from a static rocket image. Then, guided by the text prompt "the rocket launching," we generate a dynamic 4D object depicting the rocket taking off. The exhaust clouds beneath the rocket are clearly visible and rendered with high quality. In the second example, we again perform editing based on an image-to-4D representation. Starting from a static image of a spaceship, we apply the prompt "the spaceship injecting fuel." The edited 4D sequence shows a vivid blue flame jetting from the tail of the spaceship, reflecting the intended action. The final example demonstrates editing based on a text-to-4D pipeline. Given the prompts Pikachu in white t-shirt and Pikachu in black jacket, our method generates two distinct 4D objects: Pikachu wearing a white t-shirt and Pikachu dressed in a black jacket, showcasing our model's ability to control and modify appearance through text. In addition, we conducted a thorough evaluation of our model. This includes a quantitative comparison on the consistent 4D dataset for video-to-4D generation, as well as a quantitative benchmark on image-to-4D generation. In both settings, our model achieves state-of-the-art performance. To conclude, let me briefly summarize our key contributions. First, we propose a novel approach for generating high-quality, spatially and temporally consistent 4D content from monocular video. Second, our framework is the first to integrate image enhancement, inconsistency detection, and video diffusion based in painting to significantly improve visual quality. Third, our method achieves state-of-the-art performance across multiple benchmarks and demonstrates strong versatility in applications such as text and image condition 4D generation. Thank you for listening. We hope you found our work interesting and inspiring.